The first part of Chapter 7 looks at chemical reactions and chemical equations. So for the first part of this, we're going to take a chemical reaction written out in words, like for example, magnesium reacts with chlorine gas to produce magnesium chloride, and we're going to learn how to write it into a chemical equation. Before we do that, we're going to look at how we know a chemical reaction has taken place. So we're going to look at evidence of a chemical reaction. Anytime a chemical reaction or chemical change has evidence that accompanies it. So below we have 5 ways for which we can observe a reaction has taken place. So for this first one here, we have sort of a colorless solution down here. Into it, we're adding something else that appears to be colorless. And upon doing that, we get sort of this bright pink, or kind of on this, it looks orange. So we get a very different color. So for this one, when 2 different chemicals have come into contact, we see a color change. So number 1 here is color change. So color change is the first one. So the second one here, we have a liquid in the test tube, and to it we're adding another liquid, and when we do that, we produce this sort of white flaky solid. So the second way that we see that is when 2 chemicals come into contact with another, they will produce a solid. So producing a solid, 2 liquids coming together. So this isn't just say like, ooh, I took my water and I put it in the freezer and it turned into a solid. We have 2 chemicals coming into contact with one another to force a chemical change or to make a solid. So that's very important here. Okay, so number 3. So for this one here, we have this liquid, and to it we added a sort of piece of, looks like a block of solid. And when we did that, we see all these bubbles being produced. So also we can produce a gas. So the liquid and the solid come into contact with one another and we produce a gas. And so this one here is if you're familiar with this, you crack this guy open and it begins to glow. This is a glow stick. So we have produce light. So in the glow stick, they have the 2 chemicals separated, and then when you crack the thin tube of glass in there, the 2 are allowed to mix, and the result we get from that chemical reaction is the glow or the production of light. And then the 5th one here, we can also get a temperature change. So a temperature change. Okay, so again, this temperature change is when we have 2 things coming into contact with one another. So I'd have to add, for example, this one down here. If, say, this is magnesium and this is hydrochloric acid, along with the bubbles, if we felt this beaker, the beaker would feel very warm. It's an exothermic reaction, so we get the production of heat as well. We also have other reactions that, when they come into contact with each other, are endothermic. They would draw energy from the surroundings, and if we touch the beaker, it would appear, or it would feel very cold. So these are the 5 ways that we can see or observe that a chemical reaction has taken place. So the next part of this is we're going to take a chemical reaction and learn how to write out a chemical equation. So we're going to represent the reaction using symbols and arrows and sort of a nice, concise way of showing what's happening in a chemical reaction. So we're going to go through the steps here. So step 1, we're going to use the symbols of the elements and formulas of compounds in the chemical equation. So our example that we're going to go through, we just talk about these steps, is magnesium reacts with oxygen to produce magnesium oxide. So I'm going to look up magnesium on the periodic table. So magnesium is here, so we're just going to write it as Mg. So we have Mg. Oxygen, we look at the periodic table. Oxygen is right here. Oxygen is O. So we'll have our O there. And then we have the ionic compound magnesium oxide. So we're going to have to figure out that formula. So all the things we learned from chapter 5 are going to be important in this chapter, where we're getting the formulas of any sort of compounds that we have in our chemical reaction. So magnesium, when it goes into or makes a compound, is Mg2+. I know that again because it's in the second column here. And oxide is the anion of oxygen, and that is O2-. Okay, so we have Mg2+ and O2-. So these ones will form MgO. So I have magnesium that I could just look up on the periodic table. Oxygen, again, the symbol from the periodic table. This compound I had to make, we get MgO. Okay, so now we're going to start setting it up into an equation. Reactants are on the left, products are on the right. Use an arrow to separate them. Multiple reactants and multiple products are separated using a plus sign. So we have two reactants, so we're going to separate those with a plus, and they go on this left side here. So we have Mg and O. We're going to use the arrow to separate reactants from products. So our arrow always goes from reactants and points towards products, so it's always going to go this way. And then our product of MgO will be on this side. So we only have one product, so it'll just be there by itself. Okay, so step 3, write any elements in the reaction as they appear in nature. What this means is we have some elements that are monatomic and we have some that are diatomic. So we have two elements here. Magnesium, the metal, is monatomic, so we're going to keep that. Oxygen is one of those 7 that are diatomic. So our 7 are nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Remember that make that 7 here in the corner of the periodic table. And hydrogen would be the 7th one. So oxygen is diatomic. So instead of O, we're going to have O2, arrow, MgO. Okay, so elements that are diatomic, we do have to make sure we put them that way in our chemical equation. Okay, so next page, step 4, probably one of the more important ones. Balance the reaction by ensuring the same number of each element are present on each side of the equation. So we had Mg and we had O2 to give us MgO. So what balancing means is we have to have the same number of magnesiums on each side, and we have to have the same number of oxygens on each side. And this step is important. When we do this, we can't change any of the work we did on our previous steps. So meaning I can't just scratch this 2 out and call it balanced. I can't undo any of the work I did on previous steps. So the way I like to do this is list my elements of magnesium and oxygen, and I'm going to compare them on each side. So just like with subscripts, if there's nothing there, that means it's 1. So out in front of here, there's nothing. I have 1 magnesium. Over here, I also have 1 magnesium. If we look at oxygens, that subscript tells me I have 2. And over here, I have just 1. Okay, so I have 2 on this side. I have 1 on this side. So the first thing I'm going to do is ensure I have the same number of oxygens on each side. So if I have 2 on this side, the only thing I can do when I balance is change the coefficients out in front. So if I need to have 2 over there, the only thing I can really do is put a coefficient of 2 right there. When I put that 2, that now changes the magnesium. So now I have 2 magnesium, and now I have 2 oxygens. So 2 and 2. So I balanced my oxygen, but I did unbalance my magnesium. So I'm going to have 1 additional step here. We're going to take a look. So if I have 2 magnesiums on this side, I need there to be 2 on this side. I'm going to put a 2 in front of that magnesium right there. And that made 2 magnesiums. So now I have 2 magnesiums, 2 oxygens on this side. And now I have 2 magnesiums and 2 oxygens on the product side as well. So that's what we do when we balance, and we're going to take a look at that in just a little bit in a little more detail. Okay, so the last step, step 5, include the state of each reactant and product using parentheses. So we have 4 states in chemical equations: solid, liquid, gas, and we have aqueous. So aqueous, we talked about this with acids. This means dissolved in water. So dissolved in water. Okay. Okay, so if we look at our periodic table, we can get our states of our elements. For compounds, sometimes it's not entirely obvious. So let's write what we have. So we have 2Mg plus O2 arrow 2MgO. So if you look at the periodic table first, magnesium is a metal. All of them are solids except for mercury, so we know that magnesium is going to be a solid. So oxygen is a gas. And then we have MgO. So ionic compounds are all solids under sort of normal conditions here. So ionic compounds are solid unless dissolved in water, and then they become aqueous. So just on their own without water, they're solids. When we dissolve them in water, they become aqueous. And we'll talk about that. Okay, so that's the 5 steps. So this here, we're going to kind of put a nice sort of box around this. This equation represents that very first initial statement we had where it said that, sorry, my dogs want to say hi, where it says magnesium reacts with oxygen to produce magnesium oxide. So we took that statement and we turned it into this chemical equation where we have it balanced with the conservation of mass where the elements are represented on each side, and we've then included their states. Okay, so let's take a look at balancing using sort of what's called an atomic look. So we're going to kind of see what happens and why we need to balance by kind of looking at the atoms involved in a chemical reaction. So consider the reaction of methane, which is this one here, CH4, so carbon is black, and hydrogen are the sort of these gray ones, with oxygen gas, O2, so our oxygens are going to get this sort of red color as seen below. So methane reacts with oxygen to produce carbon dioxide and water, so H2O. So CH4 gas plus O2 gas gives us CO2 and H2O. Okay, so if we look at what we have, why does this violate the law of conservation of mass? So in conservation of mass, matter is neither created or destroyed in any sort of chemical or physical process. So if we look here, we have 1 carbon and 1 carbon, so that looks good. But if we look, we have 4 hydrogens and 2 hydrogens. So as written, why does that violate? It looks like we go from 4 hydrogen atoms to 2 hydrogen atoms. So as written, it sort of seems like we have kind of destroyed 2 hydrogen atoms in the process, which violates the law of conservation of mass. If we look, there's another element that does that. If we look at oxygen, there's 2 on this side, and then we have 1, 2, 3 on this side. So oxygen goes from 2 O atoms, and then we have 3 O atoms. So if we look, again, that appears to violate the law of conservation of mass, where we have not the same number of atoms that we started with. So list the elements in the reaction that violate and explain how it's a violation. So it was hydrogen and oxygen. And the explanation we sort of wrote out up here, that we went from 4 to 2, and then we went from 2 to 3. So now we want to balance the reaction by adding the proper coefficients to make sure that we've upheld the law of conservation of mass. So we're going to take our CH4, our O2, and our CO2, and our H2O. Okay, and we're going to balance this so that, again, we have upheld the law of conservation of mass. Okay, so we have carbon, hydrogen, and oxygen. So let's count it up. Carbon, 1. And again, you can go back to this, refer to this if you need to count it up. So carbon, we have 1 on the reactant side, 1 on the product side. So 1 and 1. Hydrogen, we counted this up. We have 4, and then we have 2. And then oxygen, we have 2, and then it goes to 3, 2, and moves to 3. Okay, so let's start balancing. So carbon is good. Let's move to hydrogen. So we have 4 over here and 2 over here. To make them equal, we'll need to have a coefficient of 2 here. Okay, so that doesn't change there. So now we have 2 times 2, which gives us 4. Now if we look at our oxygen, we have 2 here, and then we have 2 here. So 2 oxygens plus 2 gives us 4. Okay, so now let's look. So we have carbon balanced, we have hydrogen balanced. Now we can move to oxygen. So we have 4 on this side. To get 4 on this side, this just needs to become a 2. So we have 2 times 2, which gives us 4 oxygens. So now we have the same. We have 1 carbon on each side, 4 hydrogens, and 4 oxygens on each side to balance that. And now the law of conservation of matter or mass is upheld. The atoms, or again, think back to Dalton's atomic theory, where reactions are just rearrangement of atoms. So we have just taken all of these atoms and just rearranged them, but we couldn't leave any out. So when we rearranged them, we had to use everything on this side to make all our pieces on this side, and we had to ensure we had enough. So that's what we have here. Okay, so as balance, like what we just did, our balance reaction, what we just have, if we count it up now, that 1, we have 1 carbon on each side. Now we have 1, 2, 3, 4. And then we have 1, 2, 3, 4 oxygens, 1, 2, 3, 4 hydrogens, and 1, 2, 3, 4. So if we tally up all of our atoms, it's now balanced. So circle all of the carbon atoms. So here and here. Next, do the same with oxygen. So we'll do the same. 1, 2, 3, 4. 1, 2, 3, and 4. And then I'll use let's see, how about blue? So now our carbon, 1, 2, 3, 4, or excuse me, our hydrogen, 1, 2, 3, and 4. Okay, so they are all now the same. And our answer to this is yes. So that's what balancing does for us. It ensures that we have the same number and type of atom on each side. Okay, so a couple of tips and rules for balancing before we do some practice. First, the subscript cannot be altered when balancing an equation. So if you look back, we didn't change any of the subscripts to balance. Okay, the coefficients multiply each element in the compound. So like we did here, this 2 applied to the hydrogen to give us 4, and this 2 applied to the oxygen to give us 2 there. Coefficients are always the smallest whole number ratio that will balance the equation. So here we have 1, 2, 1, 2, but say 2, 4, 2, 4 would balance this equation. But this arrangement here is the smallest whole number. Okay, so we're always looking for the smallest whole number ratio when we use our coefficients here. Polyatomic ions can be balanced as a group when the ion is in both sides, and we'll see an example of this below. It's a little trick to make balancing a little bit easier. We can use fractions to balance diatomics, but they will need to be removed at the end. We're going to see an example of that below as well. And probably a good one here, save oxygen for the end. You're going to notice that in a lot of our chemical equations, we're going to see they're going to have a lot of oxygen, and a lot of times the oxygen will just get balanced along the way. So you never really want to start with the oxygen. Okay, so let's balance these, kind of looking at our rules. Okay, so we have H2SiCl2 plus H2O to give us H8Si4O4 plus HCl. So again, I like to write out my elements. I have H, Si, Cl, and O. Okay, so we'll count it up. I have 1, 2 hydrogens here and 1, 2 hydrogens here, which gives me 4. On this side, I have 8 plus 1 here, which gives me 9. For my Si, I have 1. On this side, I have 4. Cl, I have 2. On this side, I have 1. And then oxygen, I have 1. And on this side, I have 4. Okay. So generally speaking, when looking at this, hydrogen is here and here and here and here. I definitely do not want to start with that. So a lot of times oxygen we're going to say save till the end. In this case, because hydrogen is everywhere, I'm going to save this until the very end. I'm going to start with Si and Cl. And so we'll start right here with Si. So I have a 1 on this side, and I have 4 on this side. So to balance, I'm going to need to put a 4 here. So I'm going to put a 4 there. Let's look. It's going to change all of these things. So now we have 4 times 2, which gives us 8. And we have the 2 here, 9 and 10. So now we have 10. For our Si, just the 1 here. So 4 times 1. Now we have 4. And now we have 4 times 2, which gives us 8 fluorines. Okay, so next, let's go with Cl. I guess we're going to go next to Cl since it's just sort of in one place over here. Okay, so we have 8 Cl's on this side. So to get 8 Cl's on this side, this is going to need to be an 8. Okay, so when we do that, now we have 8 hydrogens plus another 8 gives us 16. And now our Cl's, 8 times 1, gives us 8 of those. Okay, so now we have Si balanced, we have Cl balanced. Let's move on to oxygen. So again, since hydrogen is in each one of these, I don't want to do it right yet. Okay, so if we look at oxygen, I have 4 on this side. To get 4 on this side, I'm going to have to put a coefficient of 4 here. So 4 times 2 gives me 8, plus another 8 gives me 16. And then 4 times 1 gives me 4 here. Okay, so I have coefficients on everything. So hopefully the hydrogen balance, because I'm sort of worked my way through all of these. And it looks like it did. So I have 16 on each side for hydrogen, a 4 on each side for silicon, I have 8 on each side for chlorine, and I have 4 on each side for oxygen. So here's my complete balanced equation for this one here. Okay, so this next one here, we're going to get to see a case where I have nitrate and nitrate. I have sulfate and sulfate. So we're going to see an example of using or balancing polyatomic ions as one single group. Okay, so when I list things down below, I'm going to put my aluminum, then I'm going to put nitrate, then I'm going to put sodium, and then I'm going to put sulfate. Okay, so I can balance them as a group so long as they're the same on each side. So sulfate and sulfate. Hasn't changed to sulfur dioxide or sulfite or anything else. It's sulfate and sulfate. Same with nitrate and nitrate. Okay, so let's count up what we have. So aluminum here we have 1. Over here we have 2. Nitrate we have 3. Over here we have 1. Sodium we have 2. On this side we have 1. And sulfate here we have 1. On this side we have 3. So for this one, it doesn't really matter where we start because we don't really have oxygen. So we can just start at the top and work our way down. So aluminum, we have 1 on this side and 2 on this side. We're probably going to have to choose a coefficient of 2 to go right here. So 2 for aluminum. And now we have 2 times 3, which gives us 6 NO3. Okay, if we work our way down, we go with NO3 next. So we have 6 on this side. So we need there to be 6 on this side. So this is going to have to be a 6 here. Okay, so that's going to change our sodium. This becomes a 6, and now our nitrate becomes a 6 as well. Okay, so let's move on. Let's go down now to sodium. So we have 6 on this side, so we need there to be 6 on this side. So I have 2 already. So to get 6 sodiums, I'm going to have a factor here, which when multiplied by 2 gives me 6. So that's going to be 3. So 3. So 3 times 2 gives me 6. And now if I look for my sulfate, now I have 3 sulfates. So I'm going to put a 3 right here. Okay, so I've worked my way through. Let's check and make sure we have everything. So it looks like sulfate here now is balanced. So let's make sure. So 2 aluminums, 6 nitrate, 6 sodium, and 3 sulfate. So this one, again, we were able to do by keeping these as a group. You don't have to. You can divide this up into nitrogen, sulfur, and your oxygens and go that way. But this is a trick to make things just a little bit easier. Okay, our last one for balancing practice. So we have NH3 plus O2 to give us NO plus H2O. So let's write out what we have. Nitrogen, hydrogen, and oxygen. Okay, count it up. 1. Over here for nitrogen, 1. Hydrogen, we have 3. Over here, we have 2. Oxygen, we have 2. And over here, we have 2. Okay, so nitrogen good, oxygen good. Looks like we're starting with hydrogen here. Okay, so what I notice here is all the hydrogen that's here ends up over here. So I have to choose sort of a least common multiple between these because again, all of this hydrogen makes it over here. So this subscript is 3, this one is 2, so our least common multiple is 6. So I do know that there's going to be 6 hydrogens on each side. So I'm going to change both of those to a 6. Okay, so to get 6, this one needs to be a 2. So 2 times 1 gives me a 2, and then we have 2 times 3, which gives me the 6. So over here on this side, this one is a 2, so I know this needs to be a 3. So we have 3 times 2 for our hydrogen, which gives us 6. And now if we look at our oxygen, we have 3 of those, plus this one here gives us 4. Okay, so in our first round, we balanced the hydrogen, but we unbalanced nitrogen and oxygen. So according to our rules, we should save this to the end. So let's move to nitrogen. So we have 2 here. So nitrogen is right here. So to make 2 over here, we're going to put a 2 here. So 2 times 1 gives us 2. If we look at our oxygens, we have 3 here and 2 here. So we have 3, 4, 5. So that turns to a 5. Okay, so N balanced, H balanced, we're on to O. So if we look here, we have 5 on this side. We need there to be 5 on this side. This is diatomic. There's no way to make this be 5. You have 2 options right now. So we need there to be an even number of oxygens. So you can multiply everything you've done here so far through by 2 and then balance your oxygens, or you can use the trick where we can use fractions. So I can use a fraction to balance this. Okay, so to get 5 oxygens here, I need there to be 5 halves O2. So if we look, we have the 5 here. 5 halves times 2 gives us 5. Okay, so now our equation is balanced, but we can't leave it that way. So to remove the fraction, we're going to take everything and multiply it by 2. Okay, so 2 times 2 gives me 4 NH3. 2 times 5 halves gives me 5 O2. 2 times 2 gives me 4 NO. And 2 times 3 gives me 6 H2O. So we could use the fraction to balance, but then we multiplied through by 2 to take that fraction out. Okay, so that is balancing. Okay, so we're going to do one more problem, practice all that we've learned in balancing, and that will be the end of the video, and then actually we'll just make it all the way through. There's only a little bit left. Okay, so we're going to write out a complete balanced equation for the following reactions. We're going to take everything that we just did in practice and apply it here. Sodium metal reacts with water to form hydrogen gas and aqueous sodium hydroxide. Okay, so we're going to go through our steps. So first one is to sort of write things out. What we have, sodium metal is Na, reacts with water. Water is the common name for H2O to form hydrogen gas. So hydrogen gas, if we look at hydrogen on the periodic table, it is diatomic, so H2, and then sodium hydroxide. So in a compound, sodium is Na+, hydroxide is OH-, so this would give us NaOH. Okay, so here's our symbols, elements, compounds, all of those things. So we're going to put our reactants in. So we have Na plus H2O, arrow, H2 plus NaOH. Okay, so we've combined a few steps here. We already know that our hydrogen is H2, so we put it in that way. We have our reactants on one side, products on the other, separated by our pluses. So now we're really all the way down to balancing. So we want to balance. Okay, so we can probably do this one by sort of just inspection here. So 1 sodium on each side, that's good. Hydrogen, we have 2. On this side, we have 4. So if we look at our hydrogen, 2 here, sort of 4, or 3 on this side. So 3 here and 2 here. So we're going to put a 2 right here. So we need to increase the amount of hydrogen on this side, so we're going to choose 2. So in doing this, we now unbalanced our oxygen. Now there's 2, and now we have 4 hydrogens. We can fix that problem that we still need more hydrogen now on this side and balance the oxygen together by putting a 2 here. Now if we look, we have 4 hydrogen, and then we have 1, 2, 3, 4. We have 2 oxygen and 2 oxygen here. Okay, if this is something that you don't feel comfortable doing, you can always list the elements down and balance on each side like we just did. Okay, so when we did this, we unbalanced sodium. Now there's 2 sodium. It's over here by itself, so we can put that 2 there, and that should do it. 2 sodiums, 2 sodiums, 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen. Okay, so our last part of this, we're going to put in our states. Sodium metal, so that's a solid. Reacts with water. Water is the common name for the liquid form. It says hydrogen gas, so we have H2 gas. And it told us that this forms as aqueous sodium hydroxide, so we're going to have AQ there. Look at this one. We have all our states, solid, liquid, gas, and aqueous for this reaction here. So this is taking, again, all that we just did and putting it into one nice sort of example of a problem. Okay, so to finish this out, we're going to look at what's called the aqueous state. When ionic compounds are placed into water, the compound can dissolve or stay solid. Okay, so some ionic compounds will dissolve and be aqueous, like our sodium hydroxide, some do not. Okay, so compounds that dissolve are called soluble. So our sodium hydroxide we saw in the previous example is soluble. You might be aware that, say, salt dissolves in water, so salt is soluble in water. So there are varying degrees of solubility, but for this course, compounds with aqueous phase label are soluble and dissolve into water. We'll look at things that are slightly soluble and mostly soluble in other courses. When an ionic compound dissolves into water, the cation and the anion separate and mix homogeneously to form a solution. Compounds that dissociate completely like this are called strong electrolytes. So electrolytes means we have ions in water. Okay, so when this happens, it produces ions in, we'll call it solution, but that solution is water. Okay, so write out the equation for solid NaCl dissolving in water. So here's a picture of that. When you put the solid salt into water, it breaks apart into ions. So how we write that is NaCl. We're going to put an arrow. I'm going to put H2O above the arrow. It's not reacting with the water, but we are putting the NaCl into water, so it's kind of the vessel. So when it does that, these break apart, and it forms Na plus ions that are aqueous, and it forms Cl minus ions that are aqueous as well. So this solid compound, when we put it into water, breaks apart into free-floating anions and cations. So sodium sulfate also dissolves in water or is soluble in water. So we can write out that equation as well. Na2SO4 is a solid, but when we put it into water, we're going to break apart into ions. So now to build this compound, we had 2 sodiums. So we're going to get two Na plus ions, and we're going to get 1 sulfate ion. So when we do ionic equations, your subscript for your ion is going to be your coefficient here. So we had 2 sodiums. That means when this dissolves, we get 2 sodium ions floating around. 1 sulfate, 1 sulfate. Okay, so compounds, there are some compounds that do not dissolve. So compounds that do not dissolve in water are said to be insoluble, or whatever solution you're looking at. So these remain in the solid form. This forms a heterogeneous mixture. So if we look at this one here, when these two were mixed, it formed sort of this solid here, this red solid. So this is not dissolving into water. So when we have an insoluble compound, the phase label is solid, which is S. So we would have a solid on this side, not aqueous ions, but we would have solid instead. Okay, so the way that we know if something is going to be soluble or insoluble is looking at what we call a solubility chart. So solubility chart is right here. Let's see this. Okay, so our solubility chart is in your Chapter 7 module. It looks like this here. So how we read a solubility chart is up here, it's listing our soluble ions, and down here, it's listing our insoluble ions. So what this does is it looks at these ones here. These ones are mostly soluble. So when lithium, sodium, potassium, and ammonium pair with any sort of anion, they're always soluble with no exceptions. So if we look at our anions, nitrate and acetate are always soluble. It doesn't matter what cation you pair it with, it's always going to dissolve in water. Chloride, bromide, and iodine are mostly soluble. So you can pair it with almost any cation and it will dissolve. The exceptions are silver, mercury, or lead. So when these combine with these, this will make them insoluble. So this will make those compounds, make sure, insoluble. Okay, but if it pairs with anything else that's not on this list, like zinc or magnesium or calcium or whatever, it's going to be soluble. So for sulfate, kind of same thing. Most of the time it's soluble, except when paired with calcium, strontium, barium, or lead. Okay, so these are our solubles. So these tend to form aqueous compounds in solution, or they'll dissolve. When paired with these are exceptions, it turns it into a solid. On the other hand, we have anions that tend to be insoluble, and their exceptions are going to make them soluble. So over here, most of the time, these are going to form solids. So our exceptions for hydroxide and sulfide are lithium, sodium, potassium, ammonium, and for sulfide when it pairs with a few of these other ones. And for carbonate and phosphate, again, only our lithium, sodium, potassium, and ammonium. Okay, so we over here, these exceptions will make it aqueous. Okay, so that's what we're going to use for this part right here. Okay, so we're going to use our solubility chart to see if this compound would dissolve or not in water. So the first one we have is NaI. So if we look over here, iodide is mostly soluble, so it's going to be aqueous. And we're going to look and see if sodium is an exception. It's not, so this would be soluble. So again, the product iodide mostly is soluble in water. The exceptions here are cation, so it's going to stay aqueous. So this one would be aqueous. It's soluble. Okay. So copper oxide. Oxides, aren't on the solubility chart. We'll change it to sulfides. Sulfides and oxides are very similar. So we'll change that to a sulfide. We'll do copper sulfide. So sulfides are generally insoluble, and copper is not an exception. So here I change this to sulfide. Okay, so copper sulfide. So again, sulfides tend to be solids. Copper is not an exception. This one would be solid. This is insoluble. Okay, so next we have lead to iodide, PbI2. So if we look, iodides tend to be soluble. So first we're starting with soluble. So let's look and see if lead is an exception. So lead is an exception. So when iodide pairs with lead, it turns it into an insoluble product. Okay, so this one here, this will be insoluble. It will form a solid because Pb is an exception. Okay, so lead was an exception to our solubility rules, so it is insoluble. Again, iodides are generally mostly soluble. Lead was an exception, so it turned it into a solid. Okay, finally we have NH4,3PO4, ammonium phosphate. So phosphates are generally insoluble. So we're just going to check to make sure ammonia isn't an exception. So if we look, ammonia is an exception. So when ammonium pairs with phosphate, it's going to make it aqueous. It's going to make it soluble. So over here, your exceptions do the opposite. These tend to be soluble. The exceptions over here make it insoluble. These tend to be insoluble. Your exceptions make it soluble. Okay, so your exceptions on this side make it soluble. Okay, so we had ammonium was an exception. So we're going to have a soluble product there. Okay, so this one would be aqueous. And this would be soluble. And we saw in our solubility rules that ammonium, NH4 plus, is an exception. Okay, so our ammonium was an exception. So for something like this, to know if it's soluble or insoluble, that's not something that's generally inherent. So you will want to, in this chapter, anytime it talks about solubility and solubility rules, refer to table 7.2 in the text. And this can also be found in your module. And practice, again, reading this table where these ions tend to be soluble, except when paired with these particular ions, turns them insoluble. The opposite is true down below. These tend to be insoluble, except when paired with these, these turn them into soluble products. So again, learning to read the chart is going to be important for this chapter.